Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the webinar series with academics of the ITU Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open our webinar today with Professor Qian Zhang from Hong Kong University of Science and Technology. We count on your support to make this webinar an exciting experience. So please submit your question via the Q&A channel. We will address them to our speaker during the Q&A session. After the Q&A, just announced by our avatar, I will moderate the Wisdom Corner, live lesson. So please stay online. Professor Zhang agreed to a personal chat. She will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm very pleased now to introduce Professor Ian Akilditz, Editor-in-Chief of the ITU Journal and founder and president of TRUVA from the United States. Professor Akilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. Professor Akilditz has established many research centers worldwide, including South Africa, in Spain, in Saudi Arabia, and Finland. He is Editor-in-Chief Emeritus of Impact Factor journals, highly cited and at the top of the most prestigious international rankings, visiting distinguished professor in several universities around the world. His current research activities are in 6G and 7G wireless communication systems, hologram communication, terahertz, molecular communication, Internet of Bio-Nano Things, nano networks, Internet of Things in challenged environments, and many other subjects. So it is my pleasure now to give the floor to Professor Akilditz for your opening remarks and also to introduce our speaker and moderate the Q&A session. Thank you.
Thanks a lot, Alessia. Good morning, good afternoon, and good evening all around the world from Atlanta with love. I again welcome you all to the 4th season of our ITU Journal Future and Evolving Technologies webinar series. In the first 3 seasons, We had research leaders from academia and industry, and we continue this tradition in this season also. We are happy to have again many leaders lined up in this season. One of them is today's speaker, Professor Zhang Qian. Before I present Qian, I would like to briefly talk about our journal. The objective of our journal is to bring the academic and industrial worlds together in order to establish a strong bridge between academia and industry. Our journal idea was incubated back in December 2019, and the inaugural issue was published in December 2020. It is an open access journal, no fees for readers, no fees for authors. The papers go through a rigorous review process, and we try to cover all forefront and timely research activities in the academic and industrial world. The journal is a product of a big team effort, and I would like to acknowledge them here. Sujo Onao-san, Bilal Jamusi, Alessia Malarditi, and Erika Campilongo, and many others for their work and efforts, continued support, and dedication for the success of our journal. I encourage you all to submit your papers, and also if you have ideas for special issues on popular topics, please do not hesitate to contact us. Today, I have the great pleasure to present you our speaker, Zhang Qian. First of all, on behalf of our entire journal team, I personally thank Qian to accept our invitation and give this webinar today. Qian received her BS and PhD degrees from the famous Wuhan University, China, in 1994 and 1999, respectively, all in computer science. First time I met Qian was in Beijing around 2000 when she was with the Microsoft Research Asia, Beijing. She worked there from July 1999 until 2005, where she was the research manager of the wireless and networking group. Then we met again in 2005 at Hong Kong University of Science and Technology when she just had joined them as a young assistant professor. In the meantime, she had a stellar career where she is now Tencent Professor of Engineering and Chair Professor of the Department of Computer Science and Engineering. She is also serving as the acting head of Division of Integrative System Design of Hong Kong University of Science and Technology. She's the co-director of Huawei HKUST Innovation Lab, the director of the Digital Life Research Center, and the director of Microsoft Research Asia, in short form MSRA, Information Technology Key Lab of Hong Kong University of Science and Technology. Qian has published more than 430 papers in international leading journals and key conferences. She is the inventor of more than 50 granted international patents. Her current research interests include Internet of Things, smart health, mobile computing and sensing, wireless networking, as well as cybersecurity. She is a fellow of the IEEE and a fellow of Hong Kong Academy of Engineering Science. Qian has received MIT TR 100, that is MIT Technology Review World's Top Young Innovator Award. She received the Best Paper Award in several international conferences. Qian also served as editor-chief of IEEE Transactions on Mobile Computing from 2020 to 2022. She is a member of the steering committee of IEEE Infocom Conference, which is the most prestigious conference in networking, and IEEE Transactions on Games. Without further ado, again, thanks, Qian, and let us wish to all of us an enjoyable webinar.
Okay, thank you. Thank you, Professor Diaz. So actually, it's my great honor and my pleasure to join today's talk. And thanks, Diaz, for the kind invitation. He's always my lifelong mentor. So I have been working on this field and I always follow the path that Professor Yan actually did. Starting from the wireless sensor network, wireless mesh network, cognitive radio network. There's a lot of great work he did, and then happened to be we have the common research interest. So that's why it's really, really my great honor to have the chance to be here to present our work. Let me share my screen. Yeah, so hope you can see the screen now.
Yes.
Okay, thank you. So today I want to present the work, which is a combined series of work we did recently, which titled Push the Limit of Mobile Sensing, Smart Healthcare in the Age of AIoT. So again, that's the very, very basic background. So we do see the connected IoT device growth start back to 10 years ago, starting from then up to now. And then we see such a global number of connected IoT devices are expected to grow for many years to come. So that's why there will be a lot of interesting things we can do from there. So that's why IoT itself actually contribute a lot. And then today, again, with the help of AI technology, AIoT becomes a very, very essential tool to enable many smart scenarios, including but not limited to smart home, smart healthcare, smart transportation, or even large-scale smart city. So when people are talking about those smart scenarios, one of the two fundamental supporting capability, one is sensing, understand the physical world, and the other definitely is transmitting. You collected all the interesting data you transmit out, while the 5G, 6G, and even Qian now working on 7G technology. So today, I just want to focus on one aspect, which is sensing. And we believe sensing now really getting the power to push the limit of the ubiquitous intelligence in the way that we can see various type of sensing format or sensing modality. So today I want to focus on humans. So that's why particularly looking at human surrounding related sensing technologies, you can easily imagine the wearable. Okay, you have the smart watch, smart glass, smart rings. Those actually having some sensing capability like inertial sensor, those the moving, speed, direction, and also there are SEMG related sensing capability to understand your muscle activity, which is very useful for your rehabilitation and also for the brain and then human interaction. And not only the wearables, there are also other interesting sensing modalities. Particularly, I type them as the contact-based sensing modality. For example, optical sensors, which can sense the extremely tiny vibration. You can put those sensors under your pillow, under your mattress, so as when people lie on top of the bed, on top of the pillow, we can know your heart rate, your breath rate, your kind of movement, so as knows your sleep quality, etc. So those are the contact-based solution. You don't need to wear anything. We can understand your situation. So pushing this direction more, we have other contactless sensing modality. So you don't need to ask people to wear anything and even no contacting concept, we can still know what's going on. The very typical, and then people actually interact with a lot, is the camera, vision-based sensor. If you are worried about the privacy, there are other choices for you. Those are the RF sensor, acoustic sensor, light-based sensor. And interestingly, those sensors, traditionally, they are just communication media. For example, RF, we have Wi-Fi, we have 5G surrounding us. Those signals traditionally are for communication purpose. But because of this reflecting capability or the reflecting nature, when the signal reach the target object and then get bouncing back, we have the opportunity to guess, to infer the object's activity. So that's why the traditional communication media becomes the sensing platform and has the sensing capability. So with all those different type of sensing modalities putting together, no matter it's wearable, contact-based, or even contactless sensors, we got chance to really have a better understanding about what's going on. And particularly for healthcare for human beings, we can know what's going on related to our interested person and eventually provide us a lot of intelligence. So motivated by those things, we actually are working on, my group are particularly interested on the smart healthcare. So we are particularly working on how can we leverage AIoT to empower a kind of life cycle health management. We particularly focus on when users are at home, not within the hospital, but at your home, your normal living scenario. How can we enable better healthcare for you? So we particularly interested on two types of behavior. So firstly, it's like your daily behavior, like you walking around, like we are talking, like your sleep. Those are the lifestyle, those are your daily life. And there are a lot of healthy related lifestyle, those behaviors. If we can capture them, we can monitor them in a convenient but accurate manner. There are a lot of things we can learn from there. Not only in the behavior, but also there are something, not only in the physical behavior, but there are some psychological related behavior, which can be indicated with different type of vital signs. For example, our blood pressure, our heart rate, our breath rate, our lung function level, etc. So if we can get chance to monitor, understand your lifestyle behavior and also the vital sign, what we can do is, having those information together, we can dig out and we may potentially find out some interesting disease biomarker. For example, in the past, if you are just focused on your home thing, your hospital scenario, people even though care about some disease, for example, Parkinson's disease, but we can only monitor those disease, diagnose those diseases with the hospital setup. But if now we have the capability to learn your lifestyle behavior, maybe we can figure out your daily speech actually means something already. So we can discover some new biomarkers so as we can have better, have early understanding to prevent some severe disease. So biomarker discovery is one part. The other part, more general, will be the disease progress assessment. With reasonable behavior and vital sign related understanding putting together, we may be able to know whether you are go to the severe stage. For example, you have the breath-related disease, COPD. Whether you go to the severe stage, we need to change the treatment so as visual situation better. So with all this, we will get chance to understand that better when you are at home scenario. And not only that, not only the understanding, but we can also provide you personalized intervention. For your case, whether you need to do more exercise, you should do a certain type of rehabilitation, or you should do more breath with a certain pattern. Those could be the personalized intervention because we understand you much, much better than before. And you may ask whether those interventions really fits me. Don't worry, because we have the capability to sense continuously in the way. So that's why AIoT will get chance to give you the closed loop. Whether the personalized intervention works for you well or not, check about your vital sign, check about your behavior, whether those indicate a better situation. So that's why AIoT, with the capability of sensing, data analytics, and proper AI model design, will be able to empower such a life cycle health management. So with all this, keep in mind, in my group in HKUST, we are particularly working on AIoT-based smart healthcare. And we have working on different type of diseases, different type of behaviors. All in all, from application point of view, we care about vital sign monitor, physical activity recognition. Hopefully, we can find out new biomarkers to do the better access for your disease progression and give you some digital therapy, which can fit you and get you better. So those are the applications that we're working on. What are the key technologies we have to support those applications or to enable, empower those applications? We have two sides. We need to work on both sides. First side, we need to work on more accurate, more convenient sensing modality. So I just briefly talking about wearable wise, we work on arm new inertial sensor and then also EMG based sensing capability. Contact based one, we are working on the fiber optical sensing capability, design the particular optical sensors, feature sleep scenario. And moreover, we are generally working on the contactless-based solution, looking at RF, acoustic, light-based sensing, that today I want to briefly show you some example. So we are working on the sensing modality so that we'll be able to collect more information in an accurate and then hopefully convenient manner. But if you collect a lot of information, what those information really means, so we need another part of technology to work together. So sensing modality, you put in the edge device. Edge device could have one or more sensing modality embedded so that you have multi-source of sensing data. And keep in mind, those sensing data could be quite diverse, quite heterogeneous, quality not good enough. There are a lot of information and may have noises, etc., etc. What that really means, we design proper machine learning model so as to understand our, again, application, vital sign, physical activity, and correspondingly the disease-related assessment. So when we have such an architecture, we need to keep in mind we are playing with edge device. Those edge device in nature is resource constrained. So they are limited in terms of computation, memory, and then also communication capability, etc., etc. So that's why when we are designing those learning model, we need to be very careful about the resource constraint. Pruning, compression, all those things are should we working on this. And also there's another challenge. When we are working on this particular domain, we are playing with human being. We collect data, we got information from particular user, a particular group of user. But keep in mind, we design the technology, we want those technology apply for large population. So that's why there are newcomers, new users joining. We don't want to retrain our model. So there are a lot of customization related challenges and also opportunities for our work. So generally speaking, we are working on this big picture and we particularly focus on this big picture applying to different diseases, applying to different sensing modality capabilities. So today, I want to take this opportunity to introduce some of the examples. For example, if you're looking at acoustic as a good example, I will show you some of the work we did and trying to leverage those modalities and then corresponding learning capabilities. So the first work I introduced is an earphone-based spirometry. So the whole idea is we trying to understand the lung function capability. This is extremely important during COVID time. People are so scary about that. We really, really want to see our lung function, whether it's working in a good way or not. And generally, any chronic respiratory related disease like asthma, like COPD, they all require frequent respiratory tests. Just in case you have not done the respiratory test. So generally, if you go to the hospital or go to the clinic, so with the expensive device and with the professional nurse or doctor support you, you will do this 3-step. You will inspire fully, and then you will expel with the maximal efforts, and then you inspire again. After several practice, those 3 steps, ideal situation, the expensive professional medical device will give you this flow volume curve. And actually, such a curve will show a lot. So our doctor looking at this flow volume curve, they will show the differences of normal user's behavior, or this is an asthma patient, or to a certain severe stage. And correspondingly, will also come out the non-function index, FVC, and then FVC1, etc., out of this flow volume curve. But the question is, if this such an expensive device go to the hospital or clinic frequently, just trying to access my lung function, it's too much. It's a burden. So that's why a lot of chronic disease patients suffer from lack of frequent assessment, and eventually when they go to the hospital, it's a severe stage already. So can we enable a better way so as we can, at home scenario, we can still assess our lung function in a frequent and cost-effective manner? So what's our idea is, well, looking at we have earphone, and pretty much everybody using earphone daily. So can we just enable earphones so as it has the respiratory related function? So that's why we can have such an idea. So the whole idea is coming from, we are talking to get a flow volume curve. So which means we need to have the flow rate. Once we want to get a flow rate, we need to get a speed. But it's not that easy to get speed. But the good thing is, if you're looking at the existing researchers' work, Fluid Dynamics has already published a paper to indicate that actually, if you want to get a flow rate, at airflow rate, there's a very essential, highly correlated parameter, which is airflow, or airflow sound. And sound is something we really love to play with because we are good at playing acoustic related signal. Okay, so the key observation is audio has a capability to capture the airflow sound, and that's highly related to the airflow speed, which give us the chance to get a flow rate. Okay, those observation is very, very essential. So that's why even though later on we count on the learning model, we should do explainable. We should design the model so as it's a physical meaning sound. So how can we do that? We did come out such an architecture. Okay, so we will simply collect the earphone recorded sound. And then those acoustic information, we should track its feature. So there are a lot of sophisticated signal processing part we need to play with it. We do the filter design. We need to make sure that we can understand the inhale, exhale, and inhale phase proper enough. And all this lead us to come out the signal processing related technique to work for that. After that, we have the male frequency related information as the input. Then we design the deep learning based flow volume curve estimation learning model. And keep in mind, we want to get the flow volume curve. So that's why we are doing the regression instead of the typical classification. So that's why we have a CNGIU related design to fit for the purpose. I don't want to go too much in detail, but again, I want to highlight, we need to understand the healthcare application. We need to come out something which is physically meaningful. So that's why in this particular design, we need to care about how can we have a reasonable good segmentation so as we really know that this is the inspiratory or this experience phase. Why this is particularly difficult? Because you can, every user, you can sense if you inhale, this inhale stage, the flow rate is low. When the flow rate is low, the sound actually is too weak to capture. So it's not easy to differentiate whether this is real, the inspiratory signal, or it's a noise signal, or actually there's none, there's nothing happened. So how can we differentiate that? Again, we check in very detail about its signal pattern. And we find out very interesting, these three types of signal, they have totally distinct frequency distribution. So that's why we got a chance to do the clustering algorithm so as to classify those different types of signals. And so again, we'll be able to really playing with the problem domain. And then you have your frequency related information. You design the proper learning model. Again, as I just mentioned, we have a CNGIU architecture so as to achieve the regression purpose. And so here you can see that we actually spend quite significant efforts to recruit 60 subjects. And some of them are even the quite elderly person who suffer from the chronic disease for reasonable long period of time. So we collect the data and then we compare with the GrandChoose device, which is reasonably expensive. And then for sure they pass the certificate so as their data actually, they can be the benchmark and then the standard to the GrandChoose to help us to fine tune our model. So eventually we get a very good result. Let me show a very brief video about our system. So here you can see that we actually designed the earphone, and then the earphone, there are microphone inside. And we have the Raspberry Pi running our learning model. And then what we use is the mouthpiece, just trying to make sure that we can have the same data volume as the existing medical grade device, because those devices using such a mouthpiece. And then the users just need to do exactly what you need to do to conduct a lung function test with those three phases. And when you are doing this, the system can give out the flow volume curve. And then we compare with the medical grade device and we achieve reasonable good quality. So you can see that just by playing with the acoustic as the sensing modality with the design, by understanding the problem well enough, we'll be able to enable the home-based non-functional access. But from the chronic disease point of view, understanding is not good enough. So that's why it's very natural. You should ask the question, after I understand my situation, can I do something? Should I do something? So actually, again, for COPD disease, we know that we work together with the doctors. We know that diaphragmatic breathing is a very useful technique, the breathing technique. You should use and you should exercise so as if you do that frequently at home in a proper manner, can help you to reduce the time that your disease will become severe. So training your breath muscle actually will be very helpful for you. But that's not that easy. Again, think about you do some like breath at home and somebody saying, well, you should do a diaphragmatic rather than the chest breathing. How come I can know whether I did it correct or not? Do such a practice at the rehabilitation center itself actually is not easy already, because you need a therapist to pretty much touch your breath, touch your chest, and then the hemispheres to understand whether you are doing well or not. So it's very time consuming. Not saying at your home scenario, who can give you the monitor, who can give you the suggestion. So that's why user will very easily be not able to persist such an exercise. So our idea is, why not we just enable this home-based training, just leverage the smart sensing modality or smart sensing capability we accumulated. Particularly if you have a smart speaker, and such a smart speaker will emit the ultrasonic sound, which is not here, it's not hearable from our user's point of view, but such information sent out get bouncing back, we can capture that with the microphone and will be able to sense what's going on. But actually, it's easy to say. Technology-wise, it's also reasonably difficult. The key reason is when we are breathing, actually, first of all, you should know there's somebody sitting in front of you are breathing. And moreover, if we are now want to know the breathing type, which cause the different like chest movement, which is different from just knowing the breath rate. So that's why we need to have a very detailed understanding, the fine-grained information about breath type for each breath, the breathing cycle, in expiring phase, etc. And moreover, when you are doing this breathing, you count on the signal generated by the microphone reach the human being and then bouncing back. But actually the reflecting surface is our chest, which is much larger than the movement, chest movement. So that's why very easily we have the signal superposition issue. And moreover, once we have a human being involved in our training, we will definitely facing this domain variation issue. Different people have the different shape, have different breathing capability. And if there's a newcomer joining, you never see me before, can you still have a reasonable good performance for me? So with all those challenges keep in mind, we designed such a system architecture. So again, you can see this is our prototype. We have this smart speaker to emit the ultrasonic, and then we have the microphone array to collect the reflected information. This is the user who involved in the task in the training phase. So that's why we still ask the user to wear this breath belt to collect the ground truth information. But later, when it's in the training phase, the new user come in, he doesn't need to wear anything, which is extremely important for breath exercise, because yourself, the breath capability is weak already. If you still wear anything, that's extremely tough for you. So that's why doctors extremely love to work together with us on those contactless-based solutions. So we designed the system architecture in the way that you have such a setup, and then you will collect the data. Again, as I just mentioned, you first need to make sure you can detect this is really the breath-related, respiration-related signal. So through the cross-correlation, autocorrelation related process, we'll be able to detect this as a breath signal phase. And moreover, we need to further detect Are you in the inspiring phase or expiring phase? So that's why there are phase detection. So after that, we'll continue to design the model so as it can do the classification. But breath information itself is weak. And then also we cannot collect too many users. So that's why we need a reasonable technique to help us to do the data augmentation. And then also compound diffusion technique, which can get multiple data, multiple channels information work together, will be able to achieve better accuracy. And as I just mentioned, we need to make sure our technique, our model are general enough when there's a new user joining, we still be able to perform good performance. A transfer related technique was designed into the model. So with all this, we can see that from the breath rate type and then the estimation, detection, classifications point of view, we all achieve reasonable good performance. Again, just show you a real system that using our system, what the user eventually will enjoy. So again, as I just mentioned, during the data training stage, you need a user to wear the breath belt so as to collect the ground truth information. But in the real training phase, the user no need to wear anything. Okay, you will just do your breath exercise, and then the system will report to you the breath rate, the in and then exhale ratio. More importantly, the breath type. Whether you are conducting diaphragmatic breath properly or actually you are not doing properly, then the system can give you the feedback and suggestion. And we purposely ask our user to change the mode. And you can see that the system can follow such a change and then reporting the corresponding detected breath type, ratio, and then rate accordingly. So we are playing with the acoustic. And then in terms of putting in the microphone so as to collect the airflow related correlated sound, and then to using the non-hearable inaudible information or acoustic to understand the breath type. And we interestingly figure out there's another type of acoustic information we can leverage, which is our free speech. Okay, so that's why, again, we're working with another hospital's doctor. So we're trying to see whether we can do something to help our Parkinson patient. The reason we care about our Parkinson disease patient is because such a Parkinson disease is the second most common progressive nervous system disorder, and there's no cure to it. But if you're looking at the Parkinson disease, actually it could in different stage. And the more severe stage, the user will suffer more severely, and you need to basing on the stage to adjust the treatment. But from the user's point of view, if you go to the hospital so frequently to check whether you are still in a particular stage, it's a huge burden. So that's why it's very, very natural. We need to think about from technology supporting point of view, if there's any in-home daily access solution we can provide to our user. And we're looking at actually with the recent years AIoT technology involvement, they do have some interesting discussion along this direction. So again, from Parkinson disease point of view, we have different biomarkers. For motor-related biomarker, for example, you will see the patient actually has the gait change or has the tremble happen. So that could be a biomarker. So that's why there are some people, some researchers working on how can we leverage different technique, for example, the wearables or the wireless radar ones to monitor the motor-related behavior change, motor simpleton, so as we can assess the progression of the PD patient. But actually, first of all, there's a costly to have those solutions. Moreover, this motor-related simpleton only develop in the late stage, which means early stage Parkinson's disease patient cannot use this as the biomarker. And people also working on the light behavior using the belt or the wireless radar, so to detect and then figure out, say, nighttime when you are asleep, the breath rate, the breath behavior actually could be a new biomarker for the Parkinson's disease, which is very, very impressive. But again, those actually need a real different like a deployment in terms of the supporting infrastructure. So very interestingly, we figure out actually there's a bunch of new direction, particularly using voice as a biomarker. The very good thing is because we now have the smart speaker pretty much here and there. So if we can using voice as the biomarker, it actually can be collected with the COTS, commercial off-the-shelf device. And interestingly, the voice actually is a biomarker appear in all the stages of Parkinson's disease. So that's why we have a lot of interest to explore the capability to use voice as a biomarker. But nowadays, whether there's any good research aligned the direction, the answer is yes, but not enough. The reason is when you are talking about voice as a biomarker, particularly the voice capability got impaired and a special type of sound the patient cannot pronounce properly. So that's why there are people working on particularly focus on the content that's specifically talking for the patient, for the Parkinson's disease patient. So which is what we call as a voice as a target specific content. So you need to define some content specifically fit to conduct a voice-based assessment. So which can give you the accurate result, but from user's point of view, you give me a very, very huge burden. You let me have the awareness to involve because this is a special test. Moreover, because this is a special designed content, if I do this repeatedly, then because I got familiar with the content, the accuracy actually drops significantly. So that's why we very naturally ask the question, can we do free speech? Can we just simply do free speech? If I do free speech, you don't feel burden, you don't feel people are assess you, but then I can have a good understanding about your PD progress level. So this is a very nice observation, but it's very challenging in the way that because this is a free speech, it's not a task-specific controlled content. So the accuracy will drop significantly. Moreover, because I'm doing my free speech, if you analyze my content, I have the potential privacy concern. So that's why the question to us is how can we design effective and privacy-preserving free speech-based solution? So we conduct a detailed analysis. We find out the reason actually it works not works well because of the linguistic content variation. And if this is a well-controlled content, you will see that with different feature extraction solution, we can more or less get different results, but they are reasonably good in terms of the capability for the differentiation. But if this is a free speech using different type of existing feature extraction solution, we actually will get a very poor result. So our core observation is we can leverage the pre-trained automatic speech recognition model to help us to get a better feature extraction. So the whole idea of this work is we want to leverage the pre-trained ASR model, and such a model can help us. And we utilize the pre-trained Hubert, which is a self-supervising learning model. And the rationale is we have a transformer backbone, which is suited for the sequential data. Our audio is a very natural one. And then the self-supervised learning model can enrich the feature of fidelity, which will capture the linguistic and also the human-related characteristic well. And moreover, such a model has a massive amount of pre-trained data, which actually very good for our real-world scenario. With all this considered, but we still have challenges. The very important challenge, as I just described, we are using the daily free speech. So the potential leakage in terms of the privacy leakage is something we must bear in mind. And moreover, in our real experiment, we find out actually when we go outside to collect data, the user, the population very easily go to the uneven distribution. This is very understandable. When it's in the very early stage, people were not aware of this. When go to the very severe stage, it's not that easy to find out those patients. So that's why very naturally the distribution of the user will be unevenly distributed. And moreover, even though from voice impairments point of view, we do find a different stage, we have the vocal impairment, but such a difference is very subtle. And again, normally we can only get the good neighbor from the doctor. And when the people go to see the doctor, they go to the severe stage already. So that's why we will have a sparse supervision problem. So taking all those problems, keep in mind, we have our design like this. So we designed the assess model to tackle the subtle difference from different stage, and then also the uneven distribution issue. And also we designed the split training model mechanism so as to handle the potential leakage, privacy leakage issue. So I will not go into the detail in terms of the edge side, the user side, we have the lightweight feature extractor. In terms of the crowd side, we actually have the disease access model, which leverage the deep CN with the residual connection and focus on the ST attention. Again, we care about the linkage, the privacy leakage issue. So that's why we adopt the sleep learning STEAM, which naturally has this privacy preserving capability, but we also adopt a domain adversary training component so as to make sure we leverage the pseudo acoustic unit to emit the potential leakage, the content leakage issue. So from this piece of work, we work very closely with the hospital doctors. So we enroll 100 users, and then 50, half of them are the real PD patient. And each participant, they ask just freely talk with us some like a random topic. And so that's why it's a pure free speech kind of conversation. And then we see the overall performance actually is quite good comparing with the state of art. So those are the tries that I use as an example to demonstrate that playing with the kind of acoustic modality, we can do a lot. But definitely what we can play is not limited to acoustic. Like IF, which can give us a lot of interesting capability. So I will just briefly introduce just one piece, which actually will be published in the UBCOM this year. It's not yet presented, so I want to take this opportunity to introduce this work to you. So which is we use the acoustic, we use wireless signal, particularly millimeter wave signal, to do the dry eye disease early screening. So the motivation is very simple in the way that the dry eye is mainly because the loss of stable for the tear film, and then tear frame is the thoughts produced by our blinking. And such a stable tear frame is very essential for us to see properly. So if we come to the unstable stage, that causes a lot of trouble. So in the past, if you want to find out whether I'm really suffer from dry eye or not, you need to go to the hospital for a series of professional testing, which definitely is not convenient. So that's why a lot of dry eye patients, only when they go to the severe stage, they figure that out. So that's why it's very natural we do early screening. But how can we do that? But interestingly, we talk with the doctor, we find out there are some very interesting characteristics related to the dry eye disease. So pretty much if you have a good understanding about the spontaneous blinking, and during this spontaneous blinking, if you really are the dry eye disease patient, you will have incomplete blinks, short blink interval, prolonged eyelid close time. So those are the characteristics. So anytime if you have some characteristic, we'll be loved to using the technique to capture those characteristics. So which means if I have a capability to capture the entire spontaneous blinking phase, I will be able to extract some good patterns out of it. So with this keep in mind, we come out to our overall structure. So we're using the TI millimeter wave radar in the real environment to capture the blinking behavior. And definitely we design some special pattern in terms of the millimeter wave, the chip that the frame that the wireless signal that we send out. So with this, we'll be able to detect a human seat in front of the millimeter wave radar, the sensor, and then we detect your head, and then we check about the frame chip variance. And with those frame chip variance, we'll be able to extract the biomarker that we are interested in, so as we can get a reasonable reach characteristic. So those characteristics will throw them into the deep-based learning model that we design. Again, we need to keep in mind there will be user coming. So that's why we need to consider the domain adaptation issue. And we introduce an unsupervised domain adaptation model so as we can have our model fits for the new coming user. Just give you a very quick sense. This is the real scenario and real data that we can collect. So the user, some patients just need to sit there and you do a very natural behavior. And then this wireless radar will capture your behavior. And then all the blinking, you can see that we can capture it in a very real time and accurate manner. And after we get the blink, then we further enhance the signal information by design the time domain to time frequency domain transform. And then we again putting those information in our unsupervised domain adaptation model, which has the transformer backbone, which is pre-trained from the ImageNet. And eventually we collaborate with the hospital doctors, and then we put in our device to the hospital, to the clinic, and we also put the device back to office, back to home scenario. And we recruit for 54 participants, and then half of them are the real dry eye disease patient. Interestingly, our system can achieve extremely high accuracy in terms of early screening. It's 97% in different cases. So we are continuing working on this and trying to get more fine-grained information so as we can help the doctor to do the better assisted diagnosis. So the story can continue goes on because we are working on this a lot, but today, due to the time limit, I will just quickly highlight that we have also other opportunities in the light-based scenario. Or I will not go into the details because of the time limit, but just give you a high-level picture. From light sensing point of view, we leverage the visible light, and more importantly, we leverage the invisible light, the near-infrared related spectrum, so that we'll be able to understand the object that we sending out the light related information. Again, the light actually lighting from different wavelengths. And then if you put in any object on top of it, and because the object has different nutrition in terms of the different nutrition composition, and different nutrition composition actually will have different reflection property when the spectrum go with different wavelengths. So with this, we'll be able to understand what are the objects that you are eating, putting on the smart nutritional. And particularly, we're working on a spoon, and then you have the food putting on the spoon, we know what you are eating. And then we know, with this infrared sensing, we know the food calorie, for the calorie, how much you eat, and then the corresponding calorie. And more importantly, we go even further, and then using this technique, enhance the technique, we can do the spectral reconstruction, so as we can have a very cost-effective solution, but we'll be able to analyze the baby food micronutrition. The capability is more like a professional, high resolution, the spectrometry's capability. So with all this, we're enhancing the capability, leveraging the RF, acoustic, light, and the other sensing modality to have a better understanding about our surrounding, about our human beings' healthy situation. So there are a lot of other work we are still working on. Generally, there are a lot of other open challenges also. First of all, we are playing with different type of sensing modalities. So you have different sensors, different sensor combinations. You are doing the testing, doing the training in different environment, with your home, with your office, with a different type of environment. You are playing with different subject, with different device, putting in different location. All this bring you the sensing modality, diversity, and then data heterogeneity. So once you apply this, you adopt this in a different model, you will always have the source domain, target domain, difference domain situation, how you handle that properly. Moreover, when you are playing with those devices we're talking about, you need to have the edge device at your home to help you quickly give you solution, give you the decision. Then your home device, your edge device is limited in terms of resources. How can we that our design fit well in a limited resource environment? Moreover, it's not only you come out with good design, whether you design, whether your intelligent sensing result will be smooth. So there, in the image domain, there's this quite famous example, the adversary attack, in the way that if you want to do the classification about panda and then gibbon, we can give you a very perfect model decision boundary. But if you add a little bit perturbation from human eyes point of view, this is another panda, but actually such perturbation generated sample could be the adversary sample, and then cause the decision boundary cannot fit for the case, and then misclassify this as given. So in the imaging classification domain, people figure out this issue and then come out a lot of solutions. When we are working on healthcare, is this same story? The answer is yes. We're starting to investigate this, and we figure out for the wearable scenario, when we have ECG patch, when we collect the ECG data, we find out we can come out with a DNA model to do the good classification for your ECG data. So that can easily replace or at least reduce the burden for our healthcare. But actually, we successfully demonstrate that we can add some perturbation into your ECG data. And such a perturbation generated by adding those perturbation generated ECG signal, we even give that signal to the professional doctors working on reading the ECG. They cannot know this is a fake one. So from those work, we want to draw people's attention. Intelligence are good. Signal sensing are good, but those intelligent sensing, we need to also careful about the potential robustness issue. It's not only the wearables has such a problem. For contactless, we'll have an even severe problem. For example, just now we're talking about we can use the wireless signal to do the dry eye detection. There are a lot of people working on, we can use the wireless to do the gesture recognition. Okay, the background is the essential idea is very simple. Wireless signal propagate over the air, and then we do the gesture, we do the movement, which will cause the refraction difference. And such a refraction difference could be captured by the channel state information. And if we have a reasonable good signal processing feature extraction and put into the learning model, suppose ideal situation, we should get the predicted gesture accurately. But such a design, a very essential component is a model. Such a learning model, already example we show you, image classification, we can generate adversary example. Will the wireless gesture recognition system also suffer from that? It's challenge, but our work demonstrates, yes, we can launch an attack. The fundamental reason is you can bring an attacker, a wireless device close by. And then if I'm smart enough, I could generate signals so as to emit a fake multipass. If I'm smart enough, I can emit any type of neutral refraction. Well, you can argue there are a lot of challenges because control a wireless environment is pretty much impossible. And there are a lot of detailed challenge randomness because of that. But we actually successfully demonstrate that we can propose the black box robust attack, global attack, greedy attack, which can achieve high attack successful rate. The attack successful rate can go beyond like 70%, which will be a severe attack issue. So this is pretty much the last slides I have. I think align the direction for better healthcare, better smart sensing, so as we understand health situation. There are a lot of interesting work still need to be worked on. On technology side, there are more and more opportunity we can have enhance the sensing modality. We can have new materials, we can have flexible circuits, so as we can really have the wearables. And wireless part, we can have reconfigurable intelligent surface, which can proactively change the wireless environment so as we can have a better sense about the sensing behaviors accuracy. And from model-wise, there are a lot of interesting work we can work on in the way that not only in the large model we can get the help for the large model, but we can adopt those large model in a customized way in the edge side, even in the tiny side. There are a lot of resource constraints. We need to seek how we adopt the model. And moreover, keep in mind there are privacy issue, there are robustness of your learning model issue. And those technologies eventually is helping to serve for the application. So that's why particularly for the healthcare environment, there are a lot of things can eventually serve as a health prescription. It's not only the medicine you eat, nutrition, exercise, rehabilitation, etc., etc. So how those prescription really fits for you, the digital therapy actually could be empowered because of the AIoT technology. That will give you huge opportunity to improve our health situation. So with this, I want to finish today's introduction, and I'm happy to take any question.
Thanks a lot, Qian. Very nice talk. There were many interesting ideas. I really enjoyed it, and I hope the audience also enjoyed your talk. So I'm trying to find out, are there any questions from the audience? Looks like there is none, but I can start maybe, and some others will join the Q&A session. So in your presentation, you talked about the breath monitoring section. So how practical is this? Because you had this gadget that you have to put it around your waist, and so if you do certain monitoring, it's fine. But then if you're always have to do the monitoring, that gadget or device will not be that practical, or because you have to carry that little box and also this belt around your waist or around your breast. So are you working on that, or what are you trying to do in that direction?
So thank you for the question. Actually, I didn't explain myself clearly enough in the way that, so first of all, this is something we are working with the hospitals doctors. So there are several hospitals that are now very proactively working with us. So the doctors all believe this is a very interesting direction. The reason is we are actually, eventually the solution is a contactless one. So you don't need to wear any like the breath belt in the real situation. That belt is only used to train the model, to collect the data, to train the model, and then help us to refine the model in the way that improve the accuracy. So the whole idea for that piece of work is the acoustic-based sensing. So what we really need is a smart speaker. So the smart speaker will put on the table, and you sit in front of the table. So in essence, you don't need to wear anything. So don't need to wear anything is extremely important for the breath-related disease patient, because their breathing capability is weak. If we wear something and then ask them to do exercise, actually sometimes they even cannot breathe properly. So that's why doctors are so passionate about collaborating with us, because contactless is eventually a good solution to the patient. They don't suffer from the forcing that or uncomfortable experience caused by the wearing the wearable device.
Yeah, I understand, but what will happen? Let's say there is some irregularity in the breathing, and that your system somehow detects it. So what does it help to the patient? So what will happen? So in other words, will the doctor be informed and the patient has problems with breathing, and then what?
And so for example, for the COPD patient, what the doctor really want the patient to do exercise, the breath exercise, actually there are three parts. So first, they want them to do the exercise for every day 3 to 5 minute diaphragmatic breathing. So they want them to do such an exercise. Whether you conduct it proper or not, the system can do the assessment. And then such an assessment become a report sending back to the doctor. So the doctor can know that for this particular patient, I asked him to do 5 minutes diaphragmatic breath, but actually, because of his capability, he cannot follow that properly. Even though we give them the guidance, give them the feedback, he still cannot do this properly. Then the doctor can adjust his treatment so as to help the patient better. So that's why through such a technique, first of all, we can guide the user whether you do proper or not and give him in-time feedback so as he can adjust immediately. But more importantly, we can access his capability, whether you can do it or not. If you cannot do it properly, and then the doctors knows this, doctor can adjust their treatment plan so as to feed the patient better.
Okay, so there are some questions. I have to ask the audience to put their questions into the Q&A box, please. So there are some, they put their questions in the webinar chat. So please move them to the Q&A session. There is a question from an anonymous attendee. I don't know why he wants to be anonymous. So, hi, Professor Qian. I would like to ask for a particular target health issue. How do you make judgment of the type of sensing modality to be used to collect data?
Yeah, actually, that's a kind of a good question. And what the really for this topic or for this area that we are working on, the very, very essential part is before you jump in a particular problem, a particular issue, you need to have a reasonable talking or reasonable intercommunication with the domain experts. For example, when we are working on the breath-related topics, we need to work with the doctor who are specialists in this domain. And they need to have a good conversation with us to tell us, for this type of disease, what are the behavior or the vital sign that they care the most. And with this, we figure out, well, if you want to know the movement, you want to know the internal psychology-related information, so what are the proper sensing modality that fits this situation better? So again, you need to know what's your target for a particular disease. And then with that, you come out the proper sensing modality. And then starting from there, you're working on the details about the modality design and the model design.
Okay, there's another question by Hanji Guo. Thank you for the great talk. For health applications, it may be better to provide a soft decision rather than a hard decision boundary. For example, the patient has eye dryness for an 80% probability. Is it possible for the machine learning model to output such a probability?
Well, that's again, it's a case by case. Whether this is first of all, different disease, they could have such a so-called with a certain probability whether you have such a disease or not, or the issue or not. So again, this is case by case. And for some disease, it's a reason, especially screening, it's a reasonably accurate, and then the boundary, the decision boundary actually clean enough, then you can just come out the decision. But definitely the accuracy level you will measure, you will also correspondingly report your accuracy level. But there are some other diseases, actually it's not only, not a clean enough decision boundary, there could be the like a certain probability come out. Yes, the answer is definitely yes. But again, that's a different application domain, has different nature. So again, you need to closely work on with the domain experts, understand that domain issue before you come out to the technology solution.
And there is another, thank you, Qian. There's another question by Madhavan Palan. briefly, it says feedback models with less representation are the issue. How are you tackling that?
I'm not quite sure I get the.
Me too. I don't understand what he's saying, but anyhow, so there is another. Oh, yeah. So, right. That's right. So I have been told that we can continue. So I have another question for the food intake, the last part of your talk, or one of the last parts. So you need also special sensors, right? Because the food, like the kind of like chemical and biological ingredients and all that. So are you working also on the design of those special sensors, or are you just getting off-the-shelf sensors? Or are they just theoretical concepts?
We are actually the one so far we are playing with, actually we have multiple tries already. So the work that I listed above, they are all just using the LED and then photodiode. So with LED and then photodiode array for sure. So photodiode array and LED, we actually enable those three pieces of work that I described. And we have some ongoing work. We are using the spectrum camera, so the light spectrum camera, the low cost one. So which will not only getting the LED and then also reflected information captured by the photodiode, we also get the kind of the camera idea. So it's a imaging like out of the spectrum related data. So for that part, we are working with a particular startup who are manufacturing those low-cost camera, the spectrum related camera. Yes, we are working with them on this particular device, and then again enhance the capability in terms of the different food, that nutrition, and then that we can analyze it. So we are not on for those work. On one hand, we trying to understand the nutrition. On the other hand, we also trying to understand the food quality in terms of the freshness of the meat, and also in terms of the sweet level of the fruit.
Thank you, Qian. And again, thanks a lot for the nice talk and also answering the questions well. And I would like to ask Alessia to take over for the Wisdom Corner. And thank you again. Also, thanks to the audience. Please stay here and listen to the live lessons of Professor Qian Zhang. So thank you, Qian. See you at the end of this
Thank
Wisdom.
you.
Thank you so much, Ian, for moderating the Q&A session. And thank you, Professor Zhang, for your remarkable presentation. So now it's time to move to the Wisdom Corner, live life lessons, which is based upon the idea to give a unique, a special angle to this webinar series, adding a personal touch. So if you agree, I would start with my first question.
Yes, please.
Thank you. So which is your hard-earned life lesson or even failure that you would like to share with us today that perhaps might help somebody attending the webinar?
Yeah, so it's it's always a tough job to talking about your own failure, but it's but I think I really want to share one experience. I believe an extremely nice idea, but eventually because of the constraints and then about my own awareness, understand my strengths and my capability boundary thing, eventually an extremely cool idea. Even by now, I believe it's still an extreme cool idea, but I didn't make it as cool product as I hope to do that. So that's like back to around like 12 years, I actually working on a very, again, it's a healthcare domain. I'm working on the sleep related issue. Particularly, I work on the sleep apnea. So you have this like a snowing happen, and then whether you can in a home-based scenario, instead of go to the sleep center to do the detection, to do the PSG monitor, understand your sleep quality, whether at a home scenario, you can do the early detection for people suffer from sleep apnea or SARS. So at that time, we discussed a lot with the doctor. And then the doctor told me, so the one of the golden metrics I should keep in mind is SpO2, which is blood oxygen intensity level. If that drop, that means very high probability, that means sleep apnea. So with that keep in mind, I do a lot of design and then here and there, and then I choose the to monitor this with the oximeter. So that oximeter actually has something you need to put in the finger to, you can easily think about the whole night if you keep this something there to measure your quality, that experience extremely poor. So, but at that time, because I'm a kind of a researcher scientist, we need to be very accurately get the information. I believe SpO2 is something I really should working on. So that's why we spend a lot of time designing the algorithm, and eventually we force at that time I work with somebody on a startup. We force our product to really have such a design. But later on, push to the market, we find out that's a huge burden. And especially we are talking at the user who is early stage, suffer from the apnea. So the pain point is not pain enough to let the people really afford this whole night wearing this sleep, and then late morning you get up, you feel painful for this. And that actually is something we didn't do well enough. But later on, actually reason to like several, that's a 12-year story. But recent years, I see a product, I feel so amazing about that product. The product actually is quite simple. It just detects the sound. And because you sleep apnea happen, you are snoring. And they just detect that snowing sound, and then just based on that sound, they make the decision that sleep apnea happened. It's not 100% accurate as the SpO2, but that's much, much more practical. Because the story actually, this is only half of the story. The whole story is after you detect this, we do hope we can adjust your sleep gesture. So at that time, we define a pillow. The pillow have 5 airbags. And once the SpO2 drop, sleep apnea happen, we adjust your pillow, the shape, and then the height, so as it will help you to open your airway. So that idea is very cool, but because you need to measure this, and then because we need a very accurate thing, we have 5 airbags, we adjust this and that, we have a very sophisticated algorithm. It sounds very good, but too much. So the later, after this recent years, I saw a very successful product. They just basing on the sound to detect there's a snowing happen. And once snowing happen, they also have the airbag, but their airbag is just simply detect where is your head, and then slightly turn your head a little bit. Not follow the equation, not mathematically beauty enough, but it's very practical.
Wonderful. Thank you so much for sharing this experiments with us. Thank you. I will move to my second question. In which fields and which topics would you recommend students to study nowadays? Is there any current trends or emerging areas of research that you find particularly exciting or promising?
That's always a good question. People always ask, what is the future? So I would say I'm not give the answer for a particular direction, but I would rather say it in a more like a high level general idea. I believe you should working on the problem. So real problem actually make a lot of sense. So for example, I have been passionately working on the smart healthcare for like 15 years because I find out people always, the health issues always have issues. So that's why you always have open problems waiting for you to solve. So problem driven is a very important thing. And moreover, interdisciplinary or cross-disciplinary nature is always something we should keep in mind. Particularly like the healthcare, you have to be able to talk with the doctor, understand the domain issue, and you have to know what is the reason new track, for example, sensing. Old days, the days that I'm start working on the sensing capability comparing with today, contactless sensing, very tiny, small change will be able to sense that. Technology actually keep changing. So we need to make sure that we understand the domain, we'll be able to track the new technology trend, and we'll be able to work with people. Like you looking at my research style, we need to have some ECE background, signal processing. We need to have CS nature while doing AI machine learning. And you need to also talk and work with people working on new material because they can have the flexible circuit to help you. So cross-disciplinary thing, keep that in nature, keep that in mind. I think that will be help you to be able to tackle the new problem and then make the real impact.
Thank you so much. Very clear. And would like to ask you what initially sparked your interest in your field of study and how did you pursue it? So going back to when you started being a researcher.
Yeah, I think I very appreciate the time I spent in Microsoft. So the first time I meet Ian there. At that time, the basic mindset we got is we need to tackle the real problem and we need to think about using technology to revitalize the existing world. So that's actually something you always motivate you. At the very early days, I'm working on the smartphone or mobile computing in general. At that time, I was still in Microsoft. At that time, I'm still in Microsoft, and then Microsoft, well, at that time, we still have Windows Mobile. Now there's no Windows Mobile. So we have a vision, say, well, if our technology can be used by everybody, can change other people's lives, that will be wonderful. So that's why we tend to looking at the problem, which will have real impact and which reasonably huge population will be benefit from your technology. So I think you should, the students or audience can always keep in mind that if you do something, you make the real contribution, you change people's behavior, you change people's lifestyle, you help people, then that's something worth exploring.
Wonderful, actually, and this is linked to my last question. The first one was about your failure, and the last one is about your most actually tangible contributions that you have made in your career, if you can tell us, and that had a direct impact on your life or even on others' lives that you're most proud of.
I hope I can answer. That will be something in the future. My next work.
But you're very young. You're still very young, of course.
No. Actually, I really did some work. I think I'm quite proud of them. So there are a number of them, and particularly one I'm extremely proud of is the a small technique actually has been transferred and then used in Windows core network. And that's a very fundamental work, which is high-speed TCP transmission. For that, actually, people may not feel the sense about that. So at the very beginning, when I was still in Microsoft, when we designed that protocol, so the whole idea is the transmission efficiency at that time for our reliable data transmission protocol, TCP in short, is not efficient enough if we give you large bandwidth. And at that time, we already foresee large bandwidth, high speed will be the future configuration. So how can you make your transport protocol efficient enough so as it really fully occupy the bandwidth that the physical world people, the physical layer people can offer to you? So we spent quite some time doing the research. So this is the first part. More essentially, we work with our product team very closely, and we successfully transfer that technology, and that technology has been embedded, been inputted, implemented in Windows. Think about how many people are using Windows.
Yes, unbelievable. Exactly.
So again, I think there are many other those kind of examples. I think the most important feeling, the good feeling is you do something, really people use it.
Yes, wonderful. Thank you so much. Perfect closing. I really wish to thank you for being so generous, for sharing so much about your career, your successful career. And thanks, Ian, for coming back with us. So I would like to thank both of you for this very interesting webinar. And I really appreciate your passion. Actually, what you have shared with us is really important. Thank you. Ian, your last word.
Thank you, Alessia. Again, thank you, Qian. And I hope to see you in Hong Kong or somewhere in the world. It has been a long time
I really
now.
hope you can visit us soon.
Yes, I hope so. That would be really good. So I thank you again. It was really excellent, one of these nice webinars we had. So I ask the audience to join us for the next one. We have many excellent speakers planned.
Yeah.
So Alessia, who's the next one?
Sure. We will have actually tomorrow we'll have another webinar with it's our industry webinars with industry leaders with the president of T-Mobile. But we will have our next academic webinar on the 30th of April with Professor Silvia Giordano from the University of Applied Sciences and Arts of Southern Switzerland. So please join us tomorrow and on the 30th of April. Thank you so much, everybody. Thank you again to Professor.
Okay.
Thank you. Bye-bye.
Bye. Bye-bye.